Quantum mechanics is the most successful theory in the history of science. It predicts the behavior of atoms, molecules, light, and matter with an accuracy that borders on absurd. Some of its predictions have been confirmed to 11 decimal places, which is like predicting the distance from New York to Los Angeles to within the width of a single human hair. Every piece of technology you interact with, from the phone in your pocket to the MRI machine at the hospital to the GPS satellite overhead, runs on physics that quantum mechanics got right. No experiment has ever contradicted it, not one, in nearly 100 years of trying. And yet, the physicists who use this theory every single day cannot agree on what it actually says about reality. This is not a minor academic quibble. This is not two professors arguing about footnotes. In 2025, Nature published the largest survey ever conducted of physicists' views on quantum mechanics. Over 1,100 researchers responded, and the results were remarkable. 36% favored some version of the Copenhagen interpretation. 17% favored epistemic approaches, and 36%, the same number as the plurality winner, said they had no preferred interpretation at all. When asked how confident they were that their chosen interpretation was correct, only 24% said they were confident. 1 in 4. The rest were uncertain about the meaning of the most successful theory in history. Think about that for a second. We are not talking about some speculative idea at the frontier of knowledge. We are talking about the foundation of modern physics, a theory that has been in use since the 1920s, and the people who use it professionally cannot tell you what it means. The source of all this confusion has a name. Physicists call it the measurement problem, and it is, without exaggeration, the deepest unsolved problem in all of physics. It touches questions that philosophers have debated for millennia. Does reality exist independently of observation? Is the universe fundamentally random? Or is there some deeper order we have not yet found? Is there something special about consciousness, about the act of looking, that physics needs to account for? These are not the kind of questions physicists are comfortable with. They are trained to build equations and test predictions, not to argue about the nature of existence. But the measurement problem drags them into that territory, whether they like it or not. And what makes the measurement problem so maddening is that it is not hidden. It is not some subtle effect that only shows up in exotic conditions. You can see it in one of the simplest experiments ever devised. An experiment so fundamental that Richard Feynman called it the one experiment that contains all of the mystery of quantum mechanics. The double slit experiment. Here is how it works. You set up a barrier with 2 narrow slits in it. Behind the barrier, you place a detector screen, something that records where particles land. Then you fire particles at the barrier, one at a time, and see what pattern builds up on the screen. If you do this with, say, tennis balls, the result is exactly what you would expect. Some balls go through the left slit, some go through the right slit, and you get 2 clusters on the screen behind the slits. 2 stripes. Simple. But if you do this with electrons, something very different happens. The original version of this experiment used light. Thomas Young first demonstrated it between 1801 and 1803, shining sunlight through narrow openings and observing bands of light and dark on a screen behind them. Those bands were interference patterns, and they proved that light behaves as a wave. Bright bands appeared where wave crests from the two slits arrived in sync, reinforcing each other. Dark bands appeared where a crest from one slit met a trough from the other, cancelling out. This was settled physics by the mid-1800s. But then came the 20th century, and everything got strange. In 1927, Clinton Davison and Lester Germer at Bell Labs demonstrated that electrons, which everyone had assumed were particles, also produced diffraction patterns when scattered off a crystal surface. They shared the 1937 Nobel Prize for proving that matter has wave properties, just as Louis de Broglie had predicted 3 years earlier. Klaus Jonsson at Tübingen performed the first true double-slit experiment with electrons in 1961, and the definitive version came from Akira Tonomura and colleagues at Hitachi in 1989, when they sent electrons through their apparatus one at a time. One at a time. This is the crucial part. Each electron arrives at the detector screen as a single dot, a tiny, localized click. It hits one specific spot, the way a particle should. If you watch the screen in real time, it looks random. Dots appearing here and there, with no obvious pattern. After a few dozen electrons, it still looks random. But after hundreds of electrons, something begins to emerge. After thousands, it becomes unmistakable. After Tonomura's team had accumulated around 70,000 individual detections, the screen showed a beautiful, unmistakable interference pattern. Alternating bands of many hits and few hits, exactly the pattern you would expect from waves passing through two slits and interfering with each other. But each electron went through the apparatus alone. There was no other electron to interfere with. The electron appears to have passed through both slits simultaneously, interfered with itself, and then arrived at the detector as a single particle at a single location. Already, this is bizarre. But here is where the measurement problem appears. If you place a detector at the slits to determine which slit the electron actually went through, the interference pattern disappears. Completely. You get the two-stripe pattern you would expect from particles going through one slit or the other. The simple act of acquiring information about which path the electron took destroys the quantum behavior. And it gets worse. It turns out that the interference pattern does not disappear only when you actively look. It disappears whenever which path information is available in principle, even if nobody actually checks it. In the 1990s, experiments showed that if you set up a mechanism that could, in principle, reveal which slit the particle went through, even if the information is never recorded or observed by anyone, the interference pattern still vanishes. The universe seems to know whether the information exists, whether or not anyone bothers to look at it. This is the measurement problem in its rawest form. Quantum mechanics describes particles as waves of probability that can exist in multiple states at once, passing through both slits simultaneously. But the moment you try to pin down which state the particle is actually in, the wave behavior collapses into a single definite outcome, and nothing in the theory explains why. Different interpretations of quantum mechanics offer wildly different explanations for what is happening. The Copenhagen interpretation says you simply cannot ask which slit and what pattern at the same time. They are complementary descriptions, mutually exclusive ways of looking at the same reality, and nature forbids combining them. The many worlds interpretation says the electron really does pass through both slits, and at the moment of detection, the universe splits into branches where each possible outcome occurs. The pilot wave theory says particles always have definite positions, but they are guided by a real physical wave that passes through both slits and choreographs the particle's motion from behind the scenes. All three interpretations predict exactly the same experimental results. The double-slit experiment cannot distinguish between them, and that is part of what makes the measurement problem so frustrating. It is not a problem we can solve by building a better experiment. It is a problem about what the mathematics means. But to understand why this problem runs so deep, we need to look at the mathematics itself, because the equation at the heart of quantum mechanics describes a world that is nothing like the one we actually experience. The Schrödinger equation, published by Erwin Schrödinger in 1926, governs how quantum states evolve over time, and it has three properties that create enormous trouble. First, it is deterministic. Given the quantum state at any moment, the equation tells you exactly what the state will be at any future moment. There is no randomness in the equation itself. The future is completely determined by the present. Second, it is linear. This means that if a quantum system can be in state A and it can be in state B, then it can also be in any combination of A and B simultaneously. This is what physicists call superposition, and linearity guarantees that superpositions are preserved as the system evolves. A particle that starts in a superposition of going through the left slit and going through the right slit will remain in that superposition for as long as the Schrödinger equation governs its behavior. Third, it is unitary. This means it preserves information and is reversible. Nothing is lost, nothing is destroyed, nothing is created from nothing. The evolution is perfectly smooth and continuous. Now here is the problem. When we actually measure a quantum system, what we observe violates all three of these properties. Measurement outcomes are probabilistic, not deterministic. We cannot predict which result we will get, only the probability of each possibility. The act of measurement appears to destroy superpositions, violating linearity. A particle that was in a combination of spin-up and spin-down suddenly becomes one or the other. A measurement appears to be irreversible. Once you have observed a result, you cannot undo the observation and restore the original superposition. The standard textbook resolution is called the collapse postulate, sometimes called the projection postulate, and it was formalized by John von Neumann in his 1932 book, Mathematical Foundations of Quantum Mechanics. It simply declares that upon measurement, the quantum state discontinuously jumps to one of the possible outcomes, with probabilities given by the Born rule, which Max Born proposed in 1926. The probability of each outcome is the square of the amplitude of that component in the superposition. The Born rule works beautifully. Its predictions match experiment with extraordinary precision. But the collapse postulate is not derived from anything. It is simply bolted onto the theory as an additional rule, and it flatly contradicts the Schrödinger equation. As the philosopher David Albert put it, the dynamics and the collapse postulate are in direct contradiction with one another. The collapse postulate seems to be right about what happens when we make measurements, and the Schrödinger equation seems to be wrong about what happens when we make measurements, and yet the Schrödinger equation seems to be right about what happens whenever we are not making measurements. John Bell, the physicist who would later transform the entire field, put it even more concisely. Either the wave function, as given by the Schrödinger equation, is not everything, or it is not right. That is the measurement problem in a single sentence. The mathematics describes a world of smooth, deterministic, reversible evolution. The laboratory delivers a world of abrupt, random, irreversible outcomes, and nobody knows how to get from one to the other. But wait, if this is so obvious, you might be wondering, why has it not been solved? Physicists are smart people. They have had nearly 100 years. Surely someone has figured out what measurement actually means in physical terms. They have not, and the reason why goes deeper than you might expect. The most troubling aspect of the measurement problem is that quantum mechanics provides no definition of what counts as a measurement. The theory draws a line between the quantum world, where superpositions exist and the Schrödinger equation applies, and the classical world, where we see definite outcomes. But it never tells you where that line is. It never specifies what physical process triggers the transition from quantum to classical. It never explains what makes an interaction count as an observation. Von Neumann himself demonstrated just how bad this problem is through what is now called the von Neumann chain. Consider a simple measurement. A quantum particle is measured by some apparatus, say a Geiger counter. The counter clicks or does not click. But if you treat the counter itself as a quantum system, which in principle it is since it is made of atoms, then the combined system of particle plus counter enters a superposition. The counter is now in a superposition of clicked and not clicked. To collapse this superposition, you need another measurement. So a light on the counter turns red or green. But if you treat the light quantum mechanically, now the whole system, particle plus counter plus light, is in superposition. You need another measurement. So a human observer looks at the light. But if you treat the observer's eyes quantum mechanically, you see the problem. There is an infinite chain of systems, each of which needs to be measured by the next, and quantum mechanics provides no natural stopping point. Von Neumann concluded that the boundary between the quantum and classical domains is, to use his phrase, arbitrary to a very large extent. You can place it at the measuring apparatus, or at the light on the apparatus, or at the observer's retina, or at the observer's brain. Bell was even more pointed in his 1990 paper Against Measurement, written just months before his death. He argued that the very word measurement has no place in a fundamental physical theory. It suggests a human action, an intervention from outside the system, and a fundamental theory of physics should describe the whole universe, humans included, without requiring anything to stand outside of it. Bell proposed a rough rule of thumb. When in doubt, enlarge the quantum system to include more of the environment. Eventually, adding more makes negligible difference to predictions. But he knew this was a workaround, not a solution. And this brings us to the most famous thought experiment in all of physics, the one that almost everyone has heard of and almost everyone gets wrong. Schrödinger's cat. In November of 1935, Erwin Schrödinger published a 3-part paper in the journal Naturwissenschaften called The Present Situation in Quantum Mechanics. It contained a thought experiment involving a cat in a sealed box with a radioactive atom, a Geiger counter, a hammer mechanism, and a vial of poison. If the atom decays within 1 hour, the counter triggers the hammer breaks the vial, and the cat dies. If the atom does not decay, nothing happens, and the cat lives. After one half-life, quantum mechanics says the atom is in a superposition of decayed and undecayed states. And by the linearity of the Schrödinger equation, everything entangled with the atom must also be in superposition. The Geiger counter is in a superposition of triggered and not triggered. The hammer is in a superposition of fallen and not fallen. The vial is in a superposition of broken and intact. And the cat is in a superposition of alive and dead. Now, here is the part that almost everyone gets wrong. Schrödinger was not proposing that cats can actually be alive and dead at the same time. He was not celebrating the weirdness of quantum mechanics. He was attacking it. The cat thought experiment was a reductio ad absurdum, a deliberately ridiculous scenario designed to show that the Copenhagen interpretation had a fatal flaw. Schrödinger wrote that one can even set up quite ridiculous cases using the German word burlesque, meaning farcical. He argued that while it might be acceptable to believe that a particle the size of a fraction of an atom can exist in a superposition of states, it is quite another thing to believe the same about everyday objects like cats. He was saying, in effect, look at what your theory implies when you take it seriously. Superposition of a particle? Fine. Superposition of a cat? Absurd. Therefore, something is wrong with the theory, or at least with the standard way of interpreting it. The thought experiment emerged from a correspondence with Einstein, who had suggested a similar scenario involving gunpowder in a superposition of exploded and unexploded states. Both men were probing the same wound. The Copenhagen interpretation draws a line between the quantum and classical worlds, but cannot tell you where that line is. And if you refuse to draw the line, if you let the Schrödinger equation apply to everything, including cats and counters and humans, you get superpositions of macroscopic objects that we never observe. That was the challenge in 1935. 9 decades later, it remains unanswered. We have gotten much better at understanding how the appearance of classicality emerges, and we will get to that. But the core puzzle, why we see a single definite outcome when the mathematics says all outcomes should coexist, is as open today as it was when Schrödinger put his fictional cat in that fictional box. And now, with the problem clearly stated, we need to go back further, because the arguments about what quantum mechanics means did not start with Schrödinger's cat, or even with the measurement problem as we have described it. They started with two of the greatest physicists who ever lived, arguing in hotel lobbies and conference halls across Europe for the better part of 3 decades. And the stakes of that argument turned out to be far higher than either of them realized. Albert Einstein is usually cast as the loser in this story, the aging genius who could not accept quantum mechanics, who stubbornly refused to move with the times, who spent his final decades tilting at windmills. The famous line attributed to him is, "God does not play dice." And it is usually presented as the grumpy complaint of a man who just did not like probability. that version of the story is almost entirely wrong. Einstein's actual position was far more subtle, far more prescient, and far more relevant to modern physics than the caricature suggests. What he objected to was not randomness. What he objected to was incompleteness. He believed that quantum mechanics, as formulated, did not describe all of reality, that there were elements of physical reality that the theory simply left out. And his arguments for this position were so sharp that they drove the development of quantum foundations for the next century. The phrase about dice first appeared in a letter to Max Born on December 4th, 1926. Einstein wrote that quantum mechanics is certainly imposing, but an inner voice tells him that it is not yet the real thing. The theory says a lot, but does not really bring us any closer to the secret of the old one. He is convinced, he wrote, that God does not throw dice. This was not a religious statement. Einstein's God was Spinoza's God, the lawful harmony of all that exists, not a personal deity. What Einstein meant was that he believed randomness might appear at the statistical level, the way a coin flip appears random, even though it is determined by the exact force and angle of the flip, but that it could not be fundamental. There had to be something underneath. The great debates began in earnest at the 5th Solvay Conference in October of 1927, held at the Hotel Metropole in Brussels. 29 physicists attended. 17 of them were or would become Nobel laureates. The famous photograph from that conference is one of the most remarkable images in the history of science. Planck, Marie Curie, Lorentz, Einstein, Bohr, Heisenberg, Schrödinger, Dirac, de Broglie, Born, and Pauli, all gathered in the same frame. It is the only time so many of the founders of quantum mechanics were in one room. At the conference, Einstein proposed clever thought experiments designed to show that quantum mechanics was inconsistent or incomplete. Niels Bohr countered each one, often working through the night to find the flaw in Einstein's reasoning. The exchanges became legendary. Einstein would present a scenario at breakfast. Bohr would be visibly distressed. By dinner, Bohr would have a response. By the next breakfast, Einstein would have a new challenge. The most famous exchange came 3 years later at the 6th Solvay Conference in 1930. Einstein proposed his most sophisticated challenge yet, involving a box filled with radiation and equipped with a clock-controlled shutter. At a precise time, the shutter opens briefly and lets one photon escape. By weighing the box before and after, you could determine the photon's energy via Einstein's own equation relating energy to mass. Since you also know the exact time the photon left, you would have both the energy and the time of emission with arbitrary precision, violating the energy-time uncertainty relation. Bohr was reportedly devastated when he first heard the argument. He spent an agonizing night working through it, and the next morning he presented his refutation. He used Einstein's own general theory of relativity against him. Weighing the box means it moves in a gravitational field. General relativity says moving clocks in gravitational fields run at different rates. This gravitational time dilation introduces exactly enough uncertainty in the time measurement to preserve the uncertainty relation. It was a brilliant counter. Einstein conceded the point. But he never conceded the war. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published what became known as the EPR paper, titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?" It is one of the most cited papers in the history of physics, and its argument is both simple and devastating. Consider two particles that interact and then fly apart in opposite directions. Quantum mechanics says these particles can be entangled, meaning their properties are correlated in ways that cannot be explained by any shared history or pre-existing agreement. If you measure the position of particle A, you instantly know the position of particle B, no matter how far away it is. If you instead measure the momentum of particle A, you instantly know the momentum of particle B. You can choose which property to measure, and your choice apparently determines what is real about the distant particle. Einstein's argument was this: if measuring particle A can tell you about particle B, and the particles are far enough apart that no signal could travel between them during the measurement, then particle B must have had those properties all along. Otherwise, your measurement of A is somehow instantaneously affecting B, which would violate the principle that nothing travels faster than light. Einstein called this spooky action at a distance and considered it unacceptable. Therefore, he concluded, quantum mechanics must be incomplete. There must be additional variables, hidden variables as they came to be called, that determine the outcomes of measurements in advance. Bohr's response, published the same year, is notoriously difficult to pass. He essentially argued that you cannot talk about the properties of particle B without specifying the measurement context, including what you chose to measure on the particle A. In Bohr's view, asking, "What are the properties of B independent of any measurement?" is a meaningless question. For the next 3 decades, most physicists sided with Bohr. The EPR argument was treated as a philosophical curiosity, not a serious challenge. Einstein continued to work on the problem until his death in 1955, never finding the deeper theory he sought. But Einstein was asking the right question. It just took another physicist working alone and in his spare time to transform that philosophical question into something that could actually be tested in a laboratory. John Stuart Bell was born on June 28, 1928, in Belfast, Northern Ireland. His family was working class. His mother was a dressmaker. His father sold horses. Due to financial hardship, none of Bell's siblings completed high school. Bell was the exception. He attended Queen's University Belfast, earning a degree in experimental physics in 1948 and mathematical physics in 1949. He completed his doctorate at the University of Birmingham in 1956 and joined CERN in Geneva in 1960 as a particle physicist working on accelerator design. That was his day job. Quantum foundations was what he did on the side. Bell had been dissatisfied with the Copenhagen interpretation since his student days. He found its distinction between the classical measuring apparatus and the quantum system being measured, what he called the shifty split, to be intellectually unacceptable. A fundamental theory of physics, he believed, should not require an unexplained boundary. He was also deeply influenced by David Bohm's 1952 hidden variable theory, which showed that a deterministic, hidden variable account of quantum mechanics was possible, despite von Neumann's famous 1932 proof that it was not. Bell realized that von Neumann's proof contained a subtle but fatal flaw, a hidden assumption that was not justified by physics. In 1952, I saw the impossible done, Bell later wrote. Bohm had shown explicitly how hidden variables could be introduced into quantum mechanics. For 12 years, Bell thought about these problems in his spare time. Then, in 1963, he took a sabbatical from CERN and went to Stanford and then to the University of Wisconsin. Freed from his accelerator duties, he focused on the question that had been nagging him for over a decade. The result was a 6-page paper published on November 4, 1964, titled On the Einstein-Podolsky-Rosen Paradox. It appeared in a journal called Physics Physique Physica, which was prestigious but short-lived, folding entirely in 1968. What Bell proved was this: if measurement outcomes are determined by hidden variables that are local, meaning they cannot instantaneously influence each other across space, then the correlations between measurements on entangled particles must satisfy certain mathematical constraints. These constraints are now called Bell inequalities, and quantum mechanics predicts that for certain measurement settings, these inequalities are violated. In plain language, Bell showed that Einstein's dream of a local hidden variable theory was impossible. If hidden variables exist and determine measurement outcomes in advance, they must be non-local, meaning measurement on one particle must instantaneously influence the hidden variables associated with a distant particle. There is no way around it. The mathematics is airtight. Or, to put it even more plainly, the universe cannot be both local and deterministic. You have to give up at least one of those things. Think about what this means. Locality, the idea that things over here can only be influenced by things near them and not by things far away, is one of the most basic assumptions in all of physics. It is the assumption that makes the world comprehensible. If distant events could instantaneously affect local outcomes, cause and effect would become tangled beyond recognition. Science itself depends on the ability to isolate systems and study them without worrying about unknown influences from the other side of the galaxy. Determinism, the idea that the future is determined by the present, is equally fundamental. It is the assumption that makes prediction possible, that makes physics a predictive science rather than a catalogue of surprises. Bell showed that you cannot have both. If you want to preserve locality, you must accept that measurement outcomes are not determined in advance, that they are genuinely random, and that entangled particles do not carry pre-established instructions. If you want to preserve determinism, as Bohm's pilot wave theory does, you must accept non-locality, a universe in which events on one side of the laboratory instantaneously affect events on the other side. If you want to reject both options, you must give up something else entirely, perhaps the very idea that measurements have single observer independent outcomes. This was an extraordinary result. It took a decades-old philosophical debate and converted it into a testable prediction. You could go into a laboratory, create entangled particles, measure correlations, and check whether the Bell inequalities were satisfied or violated. If satisfied, Einstein was right, and quantum mechanics was incomplete. If violated, the universe is fundamentally non-local, or reality does not work the way our intuitions suggest, or both. But almost nobody noticed. The paper accumulated fewer than a dozen citations in its first 6 years. Foundations of quantum mechanics was considered a disreputable topic, something that serious physicists did not waste their time on. The dominant attitude in the physics community was captured decades later by N. David Mermin in a 1989 column for Physics Today, where he coined the phrase, "shut up and calculate." This phrase is often misattributed to Richard Feynman, but it was Mermin, and he was characterizing an attitude, not endorsing it. Bell himself described the culture this way, writing in 1981 that many physicists had come to hold not only that it is difficult to find a coherent picture of quantum mechanics, but that it is wrong to look for one. If not actually immoral, then certainly unprofessional. Into this climate, a young French physicist named Alain Aspect decided to test Bell's theorem experimentally. When Aspect visited Bell in 1975 to discuss the idea, Bell's first question was not about the experimental design. It was, "Do you have a permanent position?" Aspect did, at the Institut d'Optique in Orsay, France, and so he went ahead. The first experimental test of Bell's inequality had actually come a few years earlier from Stuart Friedman and John Clauser in 1972 at Berkeley. They used calcium atoms to produce entangled photon pairs and measured polarization correlations. The results violated the Bell inequality by 6.5 standard deviations after 200 hours of data collection. But the experiment had significant loopholes. The polarizer settings were fixed throughout each run, meaning the particles could, in principle, know in advance what measurements would be performed and adjust their behavior accordingly. This was the so-called locality loophole. Aspect's experiments, conducted between 1981 and 1982, systematically tightened the screws. He ran 3 progressively more rigorous tests. His setup used calcium atoms excited by 2-photon laser absorption to emit pairs of entangled photons. The key experiment, published in January of 1982, with 2-channel polarizers, achieved a violation of the Bell inequality by more than 40 standard deviations. The measured value of the CHSH parameter, S, was 2.697, plus or minus 0.015. The upper limit allowed by local hidden variables is 2. Aspect's result was nearly 35% higher, but the truly groundbreaking experiment came in December of 1982. Aspect and his team addressed the locality loophole by using acousto-optical modulators that switched the polarizer orientations during the flight time of the photons. The switching happened every 10 nanoseconds or so, while light needed about 20 nanoseconds to travel between the 2 detector stations. This meant that the choice of which measurement to perform on each photon was made after the photons had already left the source, and there was not enough time for a signal traveling at the speed of light to communicate that choice to the other detector. The result was the same. The Bell inequality was violated. Local hidden variables were ruled out, at least for this particular loophole. But physicists are a careful bunch, and other loopholes remained. The detectors were not perfectly efficient. They only caught a small fraction of the photon pairs, maybe a few percent. What if the undetected photons were behaving differently? This was the detection loophole, and it meant that a sufficiently clever local hidden variable theory could still, in principle, explain the results by supposing that the detection process was biased. The switching in Aspect's experiment was also not truly random. It was periodic, which meant that a sufficiently sophisticated hidden variable theory could potentially predict the switching pattern. These might sound like nitpicking, but in physics, when you are testing a fundamental principle about the nature of reality, loopholes matter. The whole point of Bell's theorem is that it gives you a sharp, testable boundary between two visions of reality. If you want the result to be airtight, you need to close every loophole simultaneously. It took another 33 years, but in 2015, 3 independent groups finally did it. The Delft experiment, led by Ronald Hansen at the Delft University of Technology in the Netherlands, was perhaps the most elegant. Instead of using photons directly, it used a technique called entanglement swapping. 2 nitrogen vacancy defect centers in diamond crystals, separated by 1.3 kilometers, were entangled by first entangling each with a photon, then performing a joint measurement on the 2 photons at a station midway between them. The separation was large enough to close the locality loophole by a comfortable margin, and the nitrogen vacancy centers could be measured with high enough efficiency to close the detection loophole. The NIST experiment, led by Christa Schalm, used entangled photons, but with superconducting nanowire detectors that exceeded 90% efficiency, more than enough to close the detection loophole. The detectors were separated by 185 meters, and the Vienna experiment, led by Anton Zeilinger and conducted in the sub-basement of the Hofburg Castle, achieved truly extraordinary statistical significance. The p-value, the probability that local hidden variables could have produced the observed results by chance, was less than 3.74 times 10 to the negative 31st power. That is 11.5 standard deviations. For context, the discovery of the Higgs boson was announced at 5 standard deviations. All 3 experiments published within 3 months of each other in late 2015. All 3 violated the Bell inequality by overwhelming margins. All 3 closed the major loopholes simultaneously. Local hidden variables were dead. Not mostly dead. Not probably dead. Dead. In 2022, the Nobel Prize in Physics was awarded to Alan Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. The Nobel Committee's citation specifically mentioned that the laureate's work had cleared the way for new technology based upon quantum information. It was the first Nobel Prize given for work directly related to quantum foundations, the first official recognition by the highest body in physics that the questions Bell had raised were not just philosophically interesting, but scientifically essential. For a field that had spent decades being told its questions were unprofessional, it was a vindication. John Bell himself had died on October 1st, 1990, of a brain hemorrhage at the age of 62. He never received the recognition he deserved. Many physicists believe he would have shared the Nobel had he lived. The prize cannot be awarded posthumously. But here is the thing about Bell's theorem and the experiments that confirmed it. They tell us something definitive about what reality is not. Reality is not locally deterministic. There are no local hidden variables pulling the strings behind the scenes. But they do not tell us what reality is. The violation of Bell inequalities is consistent with quantum mechanics, which predicts the violations perfectly. But it is also consistent with multiple, radically different interpretations of what those violations mean. The universe could be non-local, with instantaneous influences connecting distant particles. It could be branching, with every possible outcome occurring in a separate world. It could be that reality itself is observer-dependent, with no objective facts about distant systems until they are observed. Bell's theorem closes a door. It does not open a specific new one. And while the Bell test experiments were settling one question, other experiments were raising new ones. Some of them were deeply strange. The Stern-Gerlach experiment, first performed in Frankfurt on February 8, 1922, is one of the oldest demonstrations of quantum measurement, and it reveals something essential about how observation works at the quantum level. Otto Stern and Walter Gerlach heated silver atoms to about 1,050 degrees Celsius and sent them through a strongly non-uniform magnetic field. Classical physics predicted a continuous spread of deflections on the detector screen, since the atom's magnetic moments should point in random directions. Quantum theory of the time predicted discrete splitting, but into three spots, corresponding to angular momentum values of +1, 0, and -1. What they actually saw was two spots, exactly two, with nothing in between. This was unexpected even for quantum theory. Silver atoms are in a ground state with zero orbital angular momentum, so the three-spot prediction should not have applied at all. The two-way split actually revealed electron spin, an intrinsic angular momentum that comes in only two values, +1/2 and -1/2, in units of the reduced Planck constant. But spin as a concept was not formulated until 3 years later by George Uhlenbeck and Samuel Goudsmit. Stern and Gerlach had almost discovered spin without knowing it. The experiment becomes truly illuminating when you chain multiple Stern-Gerlach devices together. Take a beam of silver atoms and pass it through a first device measuring spin along the vertical axis. You get two beams, spin up and spin down. Block the spin down beam and keep only the spin up atoms. Now pass those selected atoms through a second device, but this time measuring spin along the horizontal axis. Again, you get two beams, spin left and spin right. Select only the spin left atoms. Now pass those through a third device, measuring spin along the vertical axis again. Classical intuition says all atoms should come out spin up. After all, you selected them for spin up in the first measurement. You never did anything to change their vertical spin. All you did was look at their horizontal spin in between. But that is not what happens. The third device produces both spin up and spin down in roughly equal proportions. The horizontal measurement has destroyed the information from the vertical measurement. This is not a failure of the experimental apparatus. This is a fundamental feature of quantum mechanics. Measuring one property genuinely disturbs another. The horizontal measurement does not merely reveal the pre-existing horizontal spin while leaving the vertical spin intact. It disrupts the vertical spin, randomizing it completely. Measurement in quantum mechanics is not a passive observation. It is an active intervention that changes the system being measured. This is why the word measurement is so dangerous in quantum mechanics. In everyday language, measurement means finding out what is already there. In quantum mechanics, measurement changes what is there. and nobody can explain exactly how. But the experiments that push the measurement problem hardest are not the classic ones from the early 20th century. They are far more recent, and their implications are still being absorbed. In 1989, Daniel Greenberger, Michael Horn, and Anton Zeilinger developed an approach that does something Bell's original theorem does not. Bell's theorem is statistical. It says that over many measurements, correlations between entangled particles will exceed certain limits. You need to accumulate data and compare averages. The GHZ argument, by contrast, shows a direct logical contradiction between local hidden variables and quantum mechanics in a single run. No statistics needed. The idea uses a three-particle entangled state, now called the GHZ state. Quantum mechanics makes specific predictions about the outcomes of certain measurements on this state. If you measure the spins in three particular combinations, quantum mechanics predicts each outcome with certainty. But if you assume local hidden variables, those same predictions cannot all be true simultaneously. Specifically, the hidden variable predictions and the quantum predictions give opposite signs for one of the four measurement combinations. Not a small statistical discrepancy, a flat contradiction, +1 versus -1. If the quantum prediction is right, local hidden variables are logically impossible. Zeilinger's group first demonstrated GHZ entanglement experimentally in 2000, confirming the quantum prediction and contributing to Zeilinger's eventual Nobel Prize. The result is sometimes called Bell's theorem without inequalities, because it converts the statistical argument into an all-or-nothing logical test. Then there is the delayed choice quantum eraser, and it is one of the most misunderstood experiments in all of physics. The experiment, conducted by Yoon-Ho Kim and colleagues in 1999 and published in Physical Review Letters in January of 2000, builds on the double slit setup, but with entangled photon pairs. The core setup uses spontaneous parametric down conversion, a process where a single high-energy photon splits into two lower-energy photons that are entangled with each other. One photon, called the signal photon, travels to a detector screen. The other, called the idler photon, travels to a more complex arrangement of beam splitters and detectors. The signal photon is detected first, 8 nanoseconds before the idler photon. This is the delayed choice part. The decision about what to do with the idler photon is made after the signal photon has already been detected. Now, the idler photon encounters a system with 4 possible detectors. 2 of them, D3 and D4, are set up to preserve which path information, meaning if the idler reaches one of these detectors, you can determine which slit the signal photon came through. The other 2 detectors, D1 and D2, use a beam splitter to erase the which path information before detection. The results are striking. When you correlate signal detections with idler detections at D1 or D2, you see interference patterns. The signal photons associated with erased idler photons produce the classic wave behavior. When you correlate signal detections with idler detections at D3 or D4, you see no interference, just the clump pattern expected from particles. At first glance, this seems to suggest that a choice made about the idler photon 8 nanoseconds after the signal photon was already detected retroactively determines whether the signal photon behaves as a wave or particle. Future decisions seemingly reaching backward in time to change the past. But that is not what is actually happening, and understanding why is important. The total pattern of signal photon detections at the main screen, if you look at all of them together without sorting by which idler detector fired, shows no interference at all. It is just a broad hump. The interference pattern only appears when you post-select, when you go back and sort the signal detections into subsets based on what happened to their idler partners. And crucially, you cannot do this sorting until you have the data from both detectors, which requires classical communication that cannot travel faster than light. What this means is that nobody standing at the signal detector can see any interference pattern in real time, regardless of what happens to the idler photon. No information travels backward in time. No future event changes the past. The experiment demonstrates quantum correlations, the deep connection between entangled photons, but it does not demonstrate retrocausality. As physicist Ruth Kastner wrote, the delayed choice quantum eraser neither erases nor delays. It reveals correlations that were present all along, but only become visible when you have the complete data from both ends. But the experiment does demonstrate something profound about the measurement problem. It shows that the distinction between interference and no interference, between quantum and classical behavior, depends not on when or where a measurement happens, but on the structure of correlations in the total system. Information and the availability of information plays a fundamental role in determining whether quantum behavior manifests. Another experiment that goes straight to the heart of the measurement problem is the quantum Zeno effect, which shows that measurement does not merely reveal reality, but actively shapes it. The effect was formally proposed by Baidyanath Misra and George Sudarshan at the University of Texas in 1977, though its conceptual roots go back to Alan Turing in the 1950s. The idea is deceptively simple. If you measure a quantum system frequently enough, you can prevent it from changing state entirely. You can freeze it in place through the act of observation alone. The mathematics behind this are straightforward. For very short time intervals, the probability of a quantum system transitioning from one state to another is proportional to the square of the time elapsed, not just the time itself. This means that for tiny time intervals, the transition probability is extremely small. If you make a measurement, it resets the system to its initial state. Make another measurement a short time later, and the probability of finding it has changed is negligibly small. Keep measuring frequently enough, and the system effectively never evolves at all. Wayne Tano and colleagues at NIST provided the first clear experimental confirmation in 1990. They used trapped beryllium ions, driving transitions between energy levels with radio frequency radiation, while using laser pulses to measure which level the ions were in. More frequent measurements increasingly suppressed the transition. With enough measurements, they could almost completely prevent the ions from changing state. A 2015 experiment at Cornell by Yogesh Patil and Srivatsan Chakram was even more dramatic. Using approximately 1 billion rubidium atoms cooled to near absolute zero, they demonstrated suppression of quantum tunneling through observation. Atoms that should have tunneled through a potential barrier were prevented from doing so by repeated measurement. demonstrating what the researchers called emergent classicality, the classical world where objects stay put instead of tunneling through walls might partly emerge because the environment is constantly measuring quantum systems, preventing them from exhibiting quantum behavior. The quantum Zeno effect is the measurement problem turned on its head. Instead of asking why measurement produces definite outcomes, it shows that measurement fundamentally alters dynamics. Observation does not passively reveal pre-existing states. It actively prevents new ones from forming. And then there is Wigner's friend. This thought experiment, proposed by Eugene Wigner in 1961, takes the measurement problem and turns it into a problem about disagreements between observers, and recent experiments have shown that this disagreement may be a feature of reality, not a bug. Wigner's setup is this. His friend goes into an isolated laboratory and measures a quantum system. The system starts in a superposition. The friend looks at it and sees a definite result, say spin-up. From the friend's perspective, the measurement is done. The superposition has collapsed. There is a fact of the matter about what the spin is, but Wigner is outside the laboratory. He has not looked inside, and if he treats the laboratory, the friend, and the measured particle as one big quantum system, as quantum mechanics says he can, then from his perspective, the whole system is in a superposition. The friend is in a superposition of source spin up and source spin down. No collapse has occurred. The original thought experiment was mainly used to argue about whether consciousness plays a special role, a question we will come back to. But in 2018, physicists Daniela Frauchiger and Renato Renner at ETH Zurich showed something far more disturbing. In an extended version of the Wigner's friend scenario, with two friends and two Wigners, they proved that quantum mechanics cannot consistently describe the use of itself. Different observers, all applying quantum mechanics correctly, reach contradictory conclusions about the outcomes of measurements, not just different perspectives on the same reality. Actual logical contradictions. Kaslav Bruckner at the Vienna Institute for Quantum Optics derived a Bell-type inequality for the Wigner's friend scenario, showing that three seemingly reasonable assumptions, locality, freedom of choice, and the absoluteness of observed events, meaning that measurements have definite observer-independent outcomes, cannot all be true together. At least one must be abandoned. And then experimentalists tested it. In 2019, a team led by Massimiliano Proietti at Heriot-Watt University in Edinburgh used 6 entangled photons to create a minimal version of the extended Wigner's friend scenario. Photon polarization states served as stand-ins for the friends observing outcomes. The team tested Bruckner's inequality and found it violated by 5 standard deviations. In 2020, Kokwei-Bong and colleagues derived even stronger constraints called local friendliness inequalities and experimentally violated them as well. This work received the 2023 Paul Ehrenfest Best Paper Award for Quantum Foundations. There is an important caveat. These experiments use photons as observers, which is a significant abstraction. Lev Weidman has called this ridiculous, and Tim Maudlin has noted that nobody thinks a photon is an observer. The experiments confirm that quantum mechanics makes certain predictions about entangled systems, but whether these predictions extend to actual conscious observers performing actual measurements in actual laboratories remains an open question. Still, the theoretical result is striking. If quantum mechanics is universal, applying to observers just as it applies to photons and electrons, then the idea that measurements have single, observer-independent outcomes cannot be maintained. What is real depends on who is asking. By this point, you might be wondering whether there is any explanation at all for why the classical world looks classical when the quantum world is so strange. And in fact, there is a partial explanation, one that has transformed our understanding of the quantum to classical boundary. But it comes with a crucial limitation that physicists have been arguing about for decades. The explanation is called decoherence. The decoherence program began with a 1970 paper by H. Dieter Zeh, a German physicist who was largely ignored at the time because Foundation's research was still considered disreputable. It was developed extensively by Wojciech Zurek at Los Alamos National Laboratory, starting in the 1980s, and by the 2000s, it had become one of the most important ideas in quantum physics. Here is the core insight. In the real world, no quantum system is truly isolated. Every particle interacts with its environment, the sea of air molecules, photons, gravitational fields, and other particles that surround it. When a quantum system in a superposition interacts with its environment, the superposition does not disappear, but it becomes spread out across an enormous number of environmental particles. The delicate phase relationships that allow interference, the quantum coherence, become effectively inaccessible. It is not that the superposition collapses. It is that the superposition becomes entangled with so many environmental particles that it can no longer be observed locally. The timescales for this process are extraordinarily fast. For a dust grain floating in air, decoherence happens in about 10 to the negative 31st seconds. For a bowling ball, it is even faster. For a macroscopic object like a cat, the coherence time is so unimaginably short, something like 10 to the negative 40 seconds, that no conceivable experiment could ever detect the superposition before it decoheres. To put that in perspective, 10 to the negative 40 seconds is not just a short time. It is a time so short that it makes the Planck time, the smallest meaningful unit of time in physics, at about 10 to the negative 43 seconds, look relatively leisurely. The entire age of the universe is about 4 times 10 to the 17th seconds. The time it takes light to cross a single proton is about 10 to the negative 24 seconds. A cat-sized superposition decoheres 1,000,000 billion times faster than that. By the time a single photon of light has crossed the width of a single atom, the cat's superposition has been obliterated trillions of times over. The decoherence is so fast that the superposition effectively never exists in any practical sense. This is why you will never see a cat that is both alive and dead, not because quantum mechanics stops applying at large scales, but because the environment destroys quantum coherence with such devastating speed that no macroscopic superposition survives long enough to be noticed. The classical world emerges not because quantum mechanics breaks down, but because decoherence is ruthlessly efficient. This explains a lot. It explains why we never see macroscopic superpositions. It explains why the classical world looks classical. It explains why interference patterns disappear when you add which path detectors. the detector becomes entangled with the particle, and the environment becomes entangled with the detector, and within a fantastically short time, the coherence needed for interference has leaked away into trillions of environmental interactions. Zurek developed two additional concepts that deepen this picture. The first is einselection, short for environment-induced superselection. This addresses the question of why quantum systems decohere into specific types of states. Not all superpositions are equally fragile. States that commute with the system-environment interaction, called pointer states, are robust against decoherence. Other superpositions are rapidly destroyed. The environment effectively selects which states survive, and these selected states correspond to the classical properties we observe, things like position, momentum, and energy. Zurek called this a kind of quantum Darwinism, because just as natural selection determines which organisms thrive, environmental interaction determines which quantum states persist. The second concept is quantum Darwinism itself, which Zurek developed between 2003 and 2009. It addresses how multiple observers can agree on the same classical facts. When a quantum system decoheres, copies of information about the system's pointer state are imprinted on many fragments of the environment. Different observers can independently access different fragments and arrive at the same conclusion about the system's state. This is why the classical world has the property of objectivity, multiple observers agreeing on the same facts, even though the underlying quantum mechanics is, in some interpretations, fundamentally observer-dependent. Decoherence is real, well understood, experimentally confirmed, and essential to modern quantum physics. But there is something it does not do, and this point is critical for understanding why the measurement problem remains unsolved. Decoherence does not explain why you see one outcome instead of the other. After decoherence, the quantum state of the system plus environment is still a superposition. It is still a combination of spin up with environment in state A and spin down with environment in state B. The interference terms have become unobservable, buried in countless environmental correlations. But the mathematical state still contains both outcomes. Nothing has selected one over the other. Zurek himself has acknowledged this. Decoherence alone, he wrote, cannot solve the measurement problem. It can explain the appearance of classical behavior and the suppression of interference. It can explain why certain states are preferred, but it cannot explain why a specific observer sees a specific result. To answer that question, you need an interpretation. And so we arrive at the interpretations. After nearly a century of argument, physicists have developed at least a dozen distinct ways of understanding what quantum mechanics means. Each one resolves the measurement problem differently. Each one accepts the same experimental predictions. And each one has consequences for the nature of reality that would have been considered science fiction a generation ago. The most widely known is the Copenhagen interpretation, and the first thing to say about it is that there is no single Copenhagen interpretation. The historian Don Howard has shown that the term was essentially invented in the mid-1950s, largely by Werner Heisenberg, and it lumped together ideas from Bohr, Heisenberg, Born, and Pauli that were not entirely consistent with each other. Bohr's own views are notoriously difficult to pin down, but certain elements are clear. He believed that the wave function is a symbolic representation, a mathematical tool for calculating probabilities, not a description of physical reality. Crucially, Bohr never talked about collapse of the wave packet. That concept, popularized by Heisenberg and formalized by von Neumann, would require treating the wave function as something physically real that undergoes a physical change. Bohr rejected that framework entirely. What Bohr did insist on was complementarity, the idea that certain properties of quantum systems are mutually exclusive. You can set up an experiment to observe wave-like behavior, or you can set up an experiment to observe particle-like behavior, but you cannot do both simultaneously. These are not two aspects of the same reality that you could combine into a complete picture. They are complementary descriptions, each valid in its own experimental context, and there is no underlying reality that possesses both properties independently of measurement. Bohr was explicit that his interpretation was not about subjective observation or consciousness. He wrote that it is certainly not possible for the observer to influence the events which may appear under the conditions he has arranged. The apparatus defines the conditions for meaningful attribution of properties, but the apparatus is classical, described in classical terms, and Bohr never provided a precise boundary between the classical and quantum domains. Heisenberg's version was more subjective, emphasizing the role of the observer and the act of observation in a way that Bohr carefully avoided. This divergence has caused enormous confusion because the Copenhagen interpretation is often presented as a unified position, when in fact its founders disagreed on fundamental points. What Copenhagen does not do in any of its versions is explain the measurement problem. It either dissolves it by declaring that asking about the state of a system independent of measurement is meaningless, or it avoids it by drawing an unexplained line between quantum and classical. For many physicists, this is deeply unsatisfying. For others, it is the appropriate level of humility in the face of nature's strangeness. But there is an interpretation that takes the opposite approach entirely. Instead of adding collapse to the Schrödinger equation, it removes it. Instead of drawing a boundary between quantum and classical, it erases that boundary. And instead of accepting that measurement produces a single outcome, it insists that every possible outcome actually occurs. Hugh Everett III was 24 years old and a graduate student at Princeton when he conceived what would become the most radical interpretation of quantum mechanics ever proposed. By his own account, the idea came to him in 1954 after a slosh or two of sherry during a conversation with his classmate, Charles Misner. His insight was breathtakingly simple. What if the Schrödinger equation is always correct? What if it applies to everything, observers included, with no exceptions and no collapse? The consequence was immediate and staggering. When a physicist measures the spin of an electron, the Schrödinger equation predicts that the physicist enters a superposition, one branch where she sees spin up and another where she sees spin down. Both branches are equally real. Both versions of the physicist are equally real. The universe has split. Everett wrote that from the viewpoint of the theory, all elements of a superposition, all branches, are actual, none any more real than the rest. His advisor, John Wheeler, was intrigued but cautious. Wheeler brought the thesis to Copenhagen in 1956, where it was received with hostility. Alexander Stern dismissed it as theology. Under pressure from Wheeler to make the thesis palatable to Bohr, Everett drastically shortened it, removing explicit language about splitting and branching. The watered-down version was published in Reviews of Modern Physics in July of 1957 under the title Relative State Formulation of Quantum Mechanics. In the spring of 1959, Bohr granted Everett a series of interviews over 6 weeks in Copenhagen. By Everett's own account, it was hell. Bohr did not engage with the substance of the argument. He simply restated his own position. The two men talked past each other completely. Facing the loss of his military draft deferment, Everett took a job at the Pentagon's Weapons Systems Evaluation Group, working on nuclear war strategies. He never returned to theoretical physics. He became a successful defense contractor, made money, drank heavily, chain-smoked, and grew increasingly reclusive. He died in his sleep on July 19th, 1982, at the age of 51. His son Mark, who would later become the frontman of the rock band Eels, recalled finding his father's body and touching it, with no memory of ever having touched his father while alive. Everett's daughter, Elizabeth, died by suicide in 1996, leaving a note saying she wanted to be in the right parallel universe to be with her father. The theory was resurrected by physicist Bryce DeWitt, who embraced it in the late 1960s, coined the term many worlds, and published Everett's full unabridged thesis in 1973. Today, many worlds has substantial support, particularly among quantum cosmologists and physicists working in quantum computing and quantum information theory. The appeal is obvious. Many worlds takes the Schrödinger equation seriously and at face value. There is no collapse, no measurement problem, no mysterious boundary between quantum and classical. The mathematics is clean and unified. The cost is ontological. You have to accept that every quantum measurement causes the universe to branch, that there are inconceivably many parallel versions of reality, and that all of them are equally real. For some physicists, this is the most parsimonious interpretation because it adds nothing to the mathematics. For others, it is the most extravagant because it postulates more unobservable entities than any theory in history. The sheer number of branches is staggering. Every quantum event, every radioactive decay, every photon absorption, every molecular collision creates new branches. The number of branches grows exponentially with time. After a single second of activity in a single human brain, the number of branches created by quantum events in that brain alone would exceed the number of atoms in the observable universe by an incomprehensible margin. If many worlds is correct, the totality of reality is not just bigger than we imagined. It is bigger than anything we are capable of imagining. There are also technical problems. The preferred basis problem asks why the universe branches into states corresponding to definite positions and definite outcomes, rather than arbitrary superpositions. Decoherence provides a partial answer. The environment selects certain states over others, but whether this fully resolves the issue is debated. The Born rule problem asks what probability even means in a theory where all outcomes definitely occur. If every outcome happens, what does it mean to say that one has a 70% chance? David Wallace and other proponents have proposed decision-theoretic arguments. but critics remain unconvinced. There is another interpretation that resolves the measurement problem in a completely different way by keeping particles as particles and adding a guiding mechanism. Pilot wave theory, also known as de Broglie-Bohm mechanics, was first proposed by Louis de Broglie at the 1927 Solvay conference and independently rediscovered by David Bohm in 1952. The idea is that quantum systems have two components. There is the wave function, which evolves according to the Schrödinger equation and never collapses. And there are actual particles, which always have definite positions and are guided in their motion by the wave function according to a precise mathematical rule called the guiding equation. In this picture, the double slit experiment has a completely straightforward explanation. The particle goes through one slit, always. It has a definite trajectory at all times, but the wave function, which is a real physical field, passes through both slits and interferes with itself, creating regions of constructive and destructive interference beyond the barrier. The particle is then guided by this interference pattern into the constructive regions and away from the destructive ones. Run the experiment many times, and the pattern of where particles end up reproduces the interference pattern exactly. It is as if the particle is a surfer, and the wave function is the ocean. The surfer always occupies one specific position on the water, but the wave, spread out across the sea, determines where the surfer can go. When two sets of waves overlap and interfere, the surfer is channeled into certain paths and excluded from others. The wave goes everywhere. The particle goes somewhere specific. Together, they produce the experimental results. When you add a detector at one of the slits, the wave function changes. It no longer produces the double slit interference pattern because the detector interaction disrupts it. The particle, guided by this new wave function, no longer follows the interference-producing trajectory. The interference pattern disappears. There is no collapse. There is no measurement problem in the usual sense. Measurement is just a particular kind of physical interaction, no different in principle from any other. The particle always has a definite position. The wave function always evolves according to the Schrödinger equation, the Born rule, the probabilistic rule that tells you the likelihood of finding the particle in a given place, emerges from assuming that particle positions are initially distributed according to the square of the wave function amplitude, an assumption called the quantum equilibrium hypothesis. The theory makes exactly the same predictions as standard quantum mechanics for all known experiments. You cannot distinguish it experimentally from textbook quantum mechanics. It is fully deterministic. Given the initial positions of all particles and the initial wave function, the entire future evolution is uniquely determined. So why is it not more popular? Part of the answer is historical. Von Neumann's 1932 proof that hidden variables were impossible was widely accepted for decades, even though it was flawed. Bell showed that the proof contained an unjustified assumption, but by then, the damage was done. The physics community had absorbed the lesson that hidden variables were impossible, and many never revisited it. Part of the answer is sociological. David Bohm's personal history cast a long shadow over his scientific ideas. Bohm had worked on the Manhattan Project and was a protege of Robert Oppenheimer. In May of 1949, he was subpoenaed by the House Un-American Activities Committee. He invoked the Fifth Amendment and refused to testify against colleagues. In November of 1950, he was indicted for contempt of Congress and arrested. Princeton suspended him. Though he was acquitted in May of 1951, his contract was not renewed. Oppenheimer, once his mentor, declined to support him and opposed Einstein's suggestion to hire Bohm as an assistant, reportedly advising his former student to leave the country. Bohm left. He spent the rest of his career in exile, working in Brazil, Israel, and eventually England, far from the mainstream of American physics. His political history made his scientific ideas suspect by association. This is not speculation. The historical record is clear that Bohm's persecution affected the reception of his work, and part of the answer is physical. Pilot wave theory is explicitly and unavoidably non-local. The guiding equation depends on the entire wave function configuration instantaneously. Changing a detector setting on one side of the universe instantaneously changes the trajectory of a distant particle. This is not a bug. It is exactly what Bell's theorem requires of any hidden variable theory that reproduces quantum predictions. But many physicists find explicit non-locality uncomfortable, even though standard quantum mechanics also contains non-local correlations. Then there are the interpretations that go further than Bohm, proposing that quantum mechanics itself is incomplete and must be modified. The most developed of these are the objective collapse theories. The Ghirardi-Rimini-Weber theory, proposed in 1986, postulates that wave functions undergo spontaneous random localization events, or hits. For a single particle, these hits are extremely rare, occurring roughly once every 100 million years. The localization width is about 100 nanometers, but for a macroscopic object containing something like 10 to the 23rd particles, the effective collapse rate becomes enormous, roughly once every 10 to the negative 7th seconds, or 10 million times per second. Schrödinger's cat in the GRW theory is never in a superposition for more than a split second. Roger Penrose, independently and from a different starting point, proposed that gravity is the trigger for collapse. His argument, developed in the 1980s and 90s alongside a similar proposal by Lajos Diossi, is that a superposition of two different mass distributions is also a superposition of two different space-time geometries. General relativity, which describes the geometry of space-time, has no way to handle a superposition of geometries. Penrose argues that nature resolves this tension by collapsing the superposition on a timescale that depends on the gravitational self-energy difference between the two mass configurations. These theories are different from the other interpretations in a crucial way. They make predictions that differ from standard quantum mechanics. Spontaneous collapse events should produce faint, characteristic X-ray emissions. The GRW localization should cause a slow, measurable heating of matter. Penrose's gravitational collapse should occur at specific, calculable rates for objects of different masses. This means they can be tested, and they have been tested. Experiments at the Gran Sasso Underground Laboratory in Italy, using ultra-low background germanium detectors shielded deep underground from cosmic rays, have searched for the predicted X-ray emissions from spontaneous collapse events. The results, published between 2020 and 2024, found no signal. The simplest version of the Diossi-Penrose model is now ruled out by 3 orders of magnitude, as Quantum magazine headlined in October of 2022. Physics experiments spell doom for quantum collapse theory. Modified versions with different noise properties remain viable, but they are less theoretically motivated and require additional parameters. The most ambitious objective collapse theory is Penrose's ORC-OR, or Orchestrated Objective Reduction, developed with anesthesiologist Stuart Hameroff. This proposes that quantum computations in protein structures called microtubules inside neurons are collapsed by gravitational effects, and that these collapse events are the physical basis of consciousness. It is one of the few theories that attempts to connect the measurement problem directly to the nature of consciousness. Most physicists are skeptical. The brain is warm and wet, an environment where decoherence should destroy quantum superpositions in femtoseconds, far too fast for any computational process to exploit them. But the experimental constraints on objective collapse theories are genuinely important, regardless of whether any specific theory survives. They represent one of the few places where the measurement problem makes contact with the laboratory, where interpretive questions become empirical questions. Finally, there are interpretations that dissolve the measurement problem rather than solving it by arguing that it arises from a mistaken assumption about what quantum mechanics is trying to do. Cubism, short for quantum Bayesianism, was developed by Christopher Fuchs, Carlton Caves, and Rudiger Schack starting around 2002. Its central claim is that quantum states do not represent objective physical reality. They represent an agent's degrees of belief about the outcomes of future measurements. When you assign a wave function to a system, you are not describing what the system is doing. You are describing your own state of knowledge and expectation. In this view, collapse is not a physical process. It is simply the update of beliefs after gaining new information, no different in principle from updating your estimate of whether it will rain tomorrow after checking the weather forecast. There is no measurement problem because there is no physical collapse to explain. The Born rule is not a law of physics. It is a normative rule, a constraint on how a rational agent should set their expectations. Cubism claims to dissolve the paradoxes, the non-locality, the observer dependency, all of it. There is no spooky action at a distance because wave functions are not physical things capable of action. There is no observer dependency problem because quantum states are always relative to an agent by construction. Critics accuse Cubism of solipsism, saying it reduces physics to a theory of subjective experience. Cubists reject this charge, arguing for what they call participatory realism, a view in which reality is richer than any third-person description can capture, and where the agent is a genuine participant in nature, not a detached observer. Carlo Rovelli's relational quantum mechanics, proposed in 1996, shares some of Cubism's spirit, but arrives from a different direction. Rovelli argues that the properties of quantum systems are not absolute, but relational. There is no meaning to saying a variable has a value except relative to a particular system that has interacted with it. If system S interacts with observer O, then relative to O, S has a definite value. But relative to a third system that has not interacted with either of them, S may still be in superposition. Both descriptions are correct. They are simply indexed to different reference systems, in much the same way that simultaneity is relative in Einstein's special relativity. In relational quantum mechanics, the measurement problem dissolves because there is no absolute moment of collapse. Collapse is relative to an observer. Different observers may have different, equally valid descriptions of the same system. There is no God's eye view that contains the true state of the world. These interpretive approaches are elegant and thought-provoking. They are also deeply counterintuitive. They require giving up the idea that there is a single objective state of affairs, a way the world is, independent of anyone's perspective. For many physicists, that is too high a price to pay. For others, it is exactly the lesson that quantum mechanics has been trying to teach us all along. So where does this leave us? 100 years after the development of quantum mechanics, the measurement problem remains unsolved. The 2025 Nature survey shows that the physics community is, if anything, more fragmented than it was a decade ago. The proportion of physicists with no preferred interpretation has grown. Confidence has declined. The field is in what one commentator called a state of honest confusion. But several things have changed. First, the experimental landscape has shifted dramatically. The 2015 loophole-free Bell tests closed the door on local hidden variables with overwhelming finality. The 2022 Nobel Prize for this work brought foundational questions into the scientific mainstream for the first time in decades. The 2025 Nobel Prize went to Clark, Decoherence, and Martinez for the discovery of macroscopic quantum tunneling, validating that quantum effects operate at macroscopic scales and laying the groundwork for superconducting quantum computing. Matter wave interferometry has pushed quantum behavior to ever larger objects. In 2019, a team in Vienna demonstrated quantum interference with molecules containing thousands of atoms and masses up to 25,000 atomic mass units. In 2025, a Nature paper reported interference with sodium nanoparticles exceeding 7,000 atoms and 170,000 Daltons. These experiments are gradually closing the gap between the quantum and classical worlds, pushing into the regime where some objective collapse theories predict deviations from standard quantum mechanics. And quantum computing has made the measurement problem practically urgent. A quantum computer exploits superposition and entanglement to perform computations. Its entire operation depends on maintaining quantum coherence while performing controlled measurements at specific moments. Understanding what measurement actually is and what collapse actually does is no longer just a philosophical question. It is an engineering question that affects the design and operation of real machines. Global public investment in quantum technology has reached $55.7 billion cumulative. Private venture capital hit $3.77 billion in just the first 9 months of 2025. The measurement problem has real money riding on it. To appreciate why the experimental frontier matters so much, consider the stakes. Standard quantum mechanics predicts that superposition should work at any scale. There is nothing in the Schrödinger equation that says it stops applying at a certain mass or size. But we never see superposition of truly macroscopic objects. Is this because decoherence destroys the interference too quickly, or because something else, something not in the Schrödinger equation, actually collapses the superposition when it gets too big? This is an empirical question, and experimentalists are closing in on it. The record for the largest object placed in a quantum superposition has been steadily climbing. In 2012, a team at the University of Vienna demonstrated interference with molecules containing about 800 atoms. In 2019, they pushed this to molecules of about 2,000 atoms and masses up to 25,000 atomic mass units. The 2025 Nature result with sodium nanoparticles exceeded 7,000 atoms and 170,000 Daltons. Levitated optomechanics, a technique that suspends tiny glass beads or nanoparticles in laser beams in ultra-high vacuum, has pushed even further in some respects. Teams have cooled nanoparticles with masses of around 100 million atomic mass units to their quantum ground state, meaning the particle's center of mass motion is as still as quantum mechanics allows. A 2024 paper in Physical Review Letters proposed methods to create genuine superpositions of these particles, with their center of mass in two places at once, separated by distances large enough to be detectable. If such experiments succeed, they would push quantum superposition into a mass regime where some objective collapse theories predict failure. Penrose's gravitational collapse model, at least in its simplest form, predicts that superpositions of these masses should collapse within milliseconds. If the superposition persists, Penrose's model is wrong. If it collapses faster than decoherence predicts, something beyond standard quantum mechanics is at work. This is one of the very few places where the measurement problem touches ground, where metaphysical questions become laboratory questions, and the experiments are getting closer every year. There is one more escape route from Bell's theorem that deserves mention, because it is both the most radical and the most controversial: superdeterminism. Bell's theorem assumes three things. First, locality. The distant measurements do not instantaneously influence each other. Second, the quantum mechanical predictions, which are experimentally verified. And third, measurement independence, sometimes called freedom of choice, the assumption that the experimenters can freely choose which measurements to perform. This third assumption seems so obvious as to hardly need stating. Of course, you can choose which button to press. Of course, the particles do not know in advance what you will decide to measure. But what if they do? Superdeterminism proposes that the entire history of the universe, including the experimenter's choices, is determined by initial conditions set at the beginning of time. The particles, the detectors, and the scientists' brains are all correlated by these shared initial conditions. The experimenter's choice of measurement setting is not free. It was determined by the same physics that determined the particle's properties. In this picture, Bell's inequality is not violated because there is some spooky non-local influence. It is violated because the assumption of measurement independence is false. The statistics look the way they do because the universe was set up to produce exactly those statistics. Nobel laureate Gerard T. Hooft has advocated for this approach. Sabine Hossenfelder has argued that superdeterminism deserves more attention than it gets. But the vast majority of physicists reject it. Scott Aaronson has estimated that there would be at least 100 physicists opposing superdeterminism for every one who supports it. Bell himself considered the idea and dismissed it, viewing it as essentially a reductio ad absurdum. If the universe is conspiring to correlate your brain states with distant particle properties in just the right way to fake Bell inequality violations, then all of experimental science becomes unreliable, because your choice of what experiment to perform is never truly independent of what you are testing. The superdeterminism debate highlights just how deep the measurement problem goes. Even the apparently simple assumption that experimenters can choose what to measure turns out to be philosophically loaded. The measurement problem is not just about atoms and detectors. It is about free will, determinism, and the very possibility of experimental science. Second, the attitude toward foundational questions has changed. The shut up and calculate culture that dominated physics for decades has weakened, though it has not disappeared. John Preskill of Caltech estimates that the group of physicists seriously engaged in foundations research is perhaps a few hundred among tens of thousands, but the community is growing, especially as quantum information science brings new tools and perspectives to old questions. The Foundational Questions Institute, or FQXI, funds research into fundamental physics. Annual conferences on quantum foundations attract hundreds of participants. Papers on the measurement problem regularly appear in top journals, but resolution remains elusive, and there are good reasons to think it will remain elusive for a long time. The central difficulty is that the major interpretations, Copenhagen, many worlds, pilot wave, and the various epistemic and relational approaches are empirically equivalent. They were designed to be. They all reproduce the predictions of quantum mechanics exactly. You cannot build an experiment that distinguishes between them, because they predict the same results for every experiment. Objective collapse theories are the exception. They do make different predictions, and so far, those predictions have not been confirmed. The simplest models are being ruled out, but modified versions survive, and future experiments pushing quantum superposition to larger masses may eventually test them decisively. Some physicists hope that quantum gravity, the still unknown theory that would unify quantum mechanics with general relativity, will resolve the measurement problem. Penrose argues that gravity is the key to collapse. Others suggest that the measurement problem and the problem of quantum gravity are deeply connected and must be solved together. But loop quantum gravity and string theory, the two leading approaches to quantum gravity, both proceed without resolving the measurement problem, which suggests that it may be a separate puzzle. Tim Maudlin, a philosopher of physics at New York University, argues that several interpretations, GRW, pilot wave, and many worlds, each describe in detail how the world works. The problem is not that we lack a solution. The problem is that we have too many and no way to choose between them. The choice may ultimately be philosophical rather than scientific, a matter of which assumptions about reality you are willing to give up. Sean Carroll, a physicist at Johns Hopkins and a prominent advocate for many worlds, has noted that wave function collapse has been a looming problem for much longer and is of much wider applicability than the existence of supersymmetry. Yet the effort put into investigating the two questions is extremely disproportionate, and there is one more question lurking in the background, one that physicists approach with extreme caution, but that the measurement problem refuses to let them ignore entirely. The question of consciousness. Wigner's original argument was that consciousness causes collapse. Von Neumann's chain of measurements seemed to require a conscious observer to terminate it, and some interpretations, like cubism, place the agent, the experiencing subject, at the center of the theory. The mainstream view among physicists is deeply skeptical of any role for consciousness. Victor Stenger called quantum consciousness a myth having no scientific basis. Christoph Koch, a leading neuroscientist, has noted that the brain is warm and wet, an environment where quantum coherence should be destroyed almost instantly. And most physicists would agree that invoking consciousness to solve the measurement problem simply replaces one mystery with another. But the discomfort remains. The measurement problem, at its core, is about the relationship between what the mathematics describes and what an observer experiences. Every interpretation must say something about observers, even if only to declare them irrelevant. And the fact that nearly a century of effort has not produced a consensus suggests that something important is being missed. Perhaps the lesson of the measurement problem is not that we need a better theory, but that we need a deeper understanding of what a physical theory is supposed to do. Physics has always been about predicting the outcomes of observations, but the measurement problem forces us to ask what an observation is, what an outcome is, and who the observer is. These questions straddle the border between physics and philosophy, between the objective and the subjective, between the world as described by mathematics and the world as experienced by minds. Quantum mechanics works. It works with extraordinary precision, verified across a wider range of phenomena than any theory in history. It works for single electrons and for crystals containing trillions of atoms. It works in particle colliders and in the circuits of your laptop. It has never failed a single experimental test, and yet nobody knows what it means. Every interpretation asks you to give up something. Copenhagen asks you to give up the idea that questions about reality independent of measurement are meaningful. Many worlds asks you to accept the existence of uncountably many parallel universes. Pilot wave theory asks you to accept non-local influences spanning the entire universe. Objective collapse asks you to accept that the Schrödinger equation is wrong. Cubism asks you to accept that the wave function is not a description of reality, but of your own beliefs. Each of these sacrifices would have seemed absurd a century ago. The fact that we cannot determine which one to make is perhaps the deepest statement the measurement problem has to offer. It tells us that our intuitions about reality, the intuitions we evolved for navigating a world of medium-sized objects moving at everyday speeds, are not reliable guides to the fundamental structure of the universe. It tells us that the gap between what physics can predict and what physics can explain may be wider than we imagined. John Bell, in one of his last public lectures, was asked which interpretation he preferred. He said he felt the de Broglie-Bohm pilot wave theory was the most honest because it was clear about what existed and how it behaved, even though it required non-locality. But he also said that the question might have no answer within current physics, that a future theory might look so different from anything we can presently imagine that the measurement problem would dissolve in a new framework we do not yet possess. He may have been right. The history of physics is full of problems that seemed insoluble until someone changed the question. The problem of the luminiferous ether was not solved by finding the ether. It was dissolved by Einstein's recognition that the speed of light is the same for all observers, which made the ether unnecessary. The ultraviolet catastrophe was not solved within classical mechanics. It was dissolved by Planck's discovery that energy is quantized. Perhaps the measurement problem is the same kind of puzzle, not a question waiting for an answer, but a signpost pointing to a revolution we cannot yet see. In the meantime, every time you open your phone and it works, every time a laser reads a barcode, every time an MRI machine images a brain, you are using a theory that nobody fully understands. The equations are right, the predictions are perfect, and the meaning is a mystery. That is the measurement problem. It has been waiting for nearly 100 years. It is patient, and it is not going away. There is something humbling about all of this. Humanity has split the atom, walked on the moon, sequenced its own genome, and built machines that can process 1 billion calculations per second. We have theories that describe the first fraction of a second after the Big Bang and predict the behavior of particles to 11 decimal places. We have sent spacecraft beyond the edge of the solar system and detected gravitational waves from colliding black holes 1 billion light-years away. But we cannot explain what happens when someone looks at an electron. The measurement problem is not a failure of intelligence or effort. The people who have worked on it represent some of the greatest minds in the history of science. Einstein, Bohr, Schrödinger, Heisenberg, von Neumann, Bell, Everett, Bohm, Zeilinger, Zurek. Collectively, they span a century of sustained genius, and every one of them either failed to solve it or proposed a solution that the others found unacceptable. Perhaps that is itself the most interesting thing about the measurement problem. It sits at the exact intersection of physics, philosophy, and the nature of experience. It asks what reality is, what knowledge is, and what observation is. These are not the kinds of questions that physics was designed to answer. Physics was designed to predict the outcomes of experiments, and at that task, it has succeeded beyond anyone's imagination. The measurement problem arises precisely because physics has been so successful that it has bumped up against the limits of its own framework. The Schrödinger equation works. The Born rule works. Entanglement is real. Decoherence is real. Bell inequality violations are real. Every single prediction of quantum mechanics has been confirmed. The theory is not broken. It is just incomplete in a way that nobody can agree on. Maybe the next great revolution in physics will come from this direction. Maybe someone will find a way to derive the Born rule from deeper principles, or demonstrate that collapse is a real physical process at a specific mass scale, or prove that many worlds is not just consistent but necessary. Maybe quantum gravity will require a new understanding of measurement. Maybe artificial intelligence, trained on vast data sets of quantum experiments, will spot a pattern that human intuition has missed. Or maybe the measurement problem is permanent. Maybe it is the price we pay for living inside the universe we are trying to describe. Observers who are also part of the system they observe. Minds made of atoms, trying to understand atoms. There may be no view from nowhere, no God's eye perspective from which the measurement problem resolves into clarity. There may be only perspectives, each partial, each real within its own frame of reference, none complete. Niels Bohr once said, that anyone who is not shocked by quantum theory has not understood it. Nearly a century later, the shock has not worn off. It has deepened. The more we learn, the more we are forced to confront the possibility that reality is stranger than any of our interpretations can capture, that the universe is not obligated to make sense in the way we would like it to, and in the end, that may be the measurement problem's greatest gift. Not an answer, but a question so profound that it has forced physicists to think about the nature of reality with a precision and rigor that philosophy alone could never achieve. The measurement problem has turned metaphysics into physics. It has turned thought experiments into laboratory experiments. It has turned a 100-year-old argument between two men in Brussels into a $60 billion global research program. The cat is still in the box. Nobody knows if it is alive or dead, and the greatest minds on earth are still arguing about what those words even mean.